Hi everyone, it's Ms. Howell again. I'm going to go over the assignment from March 30th. Yep, that's right. Today is Tuesday the 31st, and I had assigned a free response question on fluid mechanics in class kick. It's quite difficult, and I'm going to do my best to go over it in a way that will make sense to you. So we'll see what you think. I'd also like to remind you that these AP questions are very difficult. They're designed to be difficult. Um, they are designed so that, wow, got some interesting focus things going on here. It's designed so that, the average score is 50%. So we're going to do our best to do better than that. And I think we've got time to practice. And so we're just going to put in the work to practice, and we're going to get better and better at this stuff. So I'm going to switch out into this answer. Actually, I'm going to look in Notability here. There we go. So first of all, notice this first question is worth 12 points. I'll do some highlighting here. It's worth 12 points, and it's suggested that you take 25 minutes on this. Okay, so it says 2 students are given a spherical balloon. Now, spherical means that it's actually a sphere. I'm going to make this a little bit narrower. That has a long string attached and is filled with an unknown gas whose density is referred by the variable rho sub g. So you'll see that in some of my calculations down here. To get the mass of the gas, for example, you would take the density of the gas times the volume of the balloon. The filled balloons each have a radius referred to by the variable r, and the volume referred to by the variable v. So here I drew a picture of one of the balloons. I really should have drawn a sphere. The radius is r, and the volume is v. And again, remember that density is mass over volume. So mass would be equal to density times volume. The fitted balloons have a, let's see, blah, blah, blah. Okay, a small valve is fitted to each balloon to allow the balloon to be deflated in a controlled manner. So we are able to let air out. I shouldn't say air. Let gas out in a controlled manner. Okay, the string and the balloon itself, not including the gas, have a combined known mass of mb. Okay, mass of balloon and string mb. Derive an expression for the acceleration of the balloon when it is released in terms of the given quantities and the physical constants as appropriate. Air resistance is negligible, and the known density of air is rho sub a. Okay, so let's think about this for a second. We've got the density of the gas. We've got the density of the air. We know the mass, we know the mass of the balloon and the string. So the first thing that I decided to do to solve this question was I decided to draw a force diagram. So I drew the balloon, and then I drew in 2 forces. I drew in the buoyant force, and the buoyant force is equal to the weight of the air displaced. When we studied buoyancy, we were used to thinking about the weight of the water displaced when we were thinking about a floating object. Now this object is floating in air, so it's the weight of the air displaced. And then the downward force that we have here is F sub g, and that is the weight of the whole, this F sub g here is the weight of the balloon plus the weight of the gas inside the balloon. So this is the balloon plus the gas. Okay, so next I'm going to write my net force formula. And what I'm going to do is take the larger value minus the smaller value. So the larger value is FB. So I'm going to take the buoyant force minus the force of gravity. And now I'm going to make a whole bunch of substitutions. So I wrote my substitutions over on the right. And honestly, when I was working through this problem, I had to really think about what are all of the variables. So the first thing that I determined was that the buoyant force is, again, equal to the weight of the displaced air. And the weight of the displaced air would be equal to the mass of the displaced air times g. And then, using the definition of density, mass is density times volume. I said that the mass of the displaced air must equal the density of the air times the volume. And then I have to multiply that by g to turn that into a weight, or into a force, pardon me. So this is 1 point in the answer key from the College Board. That's 1 point for calculating that buoyant force. And then I substituted that buoyant force over here. The buoyant force is rho Vg. Okay. Next, I started to think about, well, what is Fg? So what is this Fg here? So I had to remember that Fg was the mass of the balloon and the gas added together times 9.81. In the answer key, this is also worth 1 point, figuring out that Fg is equal to the mass of the balloon plus the gas times g. And so, let's see. They tell us that the mass of the balloon plus the gas, they gave us that value. Oh yeah, that was MB. So when I made my substitutions here for F net is equal to the mass times acceleration. Well, the mass is the mass of the balloon, which is MB, that's the balloon, plus the mass of the gas inside the balloon. The mass of the gas inside the balloon is the density of the gas times the volume. And then the times acceleration. That's Newton's second law. Okay, I already had worked out this next term, so I'm just going to move on. And then for Fg, I've got the mass of the balloon plus the mass of the gas. So again, the mass of the balloon is mb, and then the gas is the density of gas times the volume. So if you can get this written right here, if you can get that written, you are doing great, because the last step is just to rearrange it. The last step is just to solve for A. And when we solve for A, we get the equation that I've written there. Okay, let's try the next part. Question B says, the first student is given a stopwatch and a tape measure and asked to use only this equipment in an experiment to determine the density of the gas inside the balloon from a graph of the data. Describe an experimental procedure that a student can use to accomplish this. Okay, so the density of the gas inside the balloon. So if I go back, the density of the gas inside the balloon is rho sub g. So one thing that we could change in order to determine rho sub g is we could determine the acceleration of the balloon. If we were to change the acceleration of the balloon, that would that would go with the changing density of the gas. So if you think about the balloon, depending on how full it is, that's going to change the density of the gas inside. Now the density of air is not going to change, and the mass of the balloon is not going to change. G is not going to change. And we would be able to measure V, the volume. So we would need to measure acceleration, volume, and and then hopefully that would get us the density. Somehow that would get us the density. By the way, we know that the density of the gas would be equal to the mass of the gas divided by the volume of the gas. Okay, so with that in mind now, I can write out my some ideas for some steps. First of all, we're going to need to get the volume of the gas. And to get the volume of the gas, I would need the radius, because I know that the volume would be 4/3 pi r cubed. So the easiest way I think to get the radius would be to use a tape measure to measure the diameter of the balloon. You could add here that you might divide circumference by 2 pi to get r, and then volume is going to be equal to 4/3 pi r cubed. You could add that, but that was not required in the answer key from the College Board. Okay, next, the next thing that you know that you need to get is you need to get the acceleration of the balloon. I'm assuming, by the way, that I already have what am I assuming? I'm assuming that I already have the mass of the balloon itself and the string still, like I did before. So now I want to think about how would I get the acceleration. So to get the acceleration, I could use delta x equals 1/2 a delta t squared. So I would need a distance, that would be my delta x, and I would need time. And that would give me acceleration. Okay, and then from those quantities, I should be able to determine the density of the gas if I change the amount of gas inside the balloon, because I'm going to get a different radius and I'm going to get a different acceleration. So these were the 4 components that you had to have in your answer to get 4 points on this. Okay. So here's an alternative way to do the experiment. A second student is given a force sensor, and the student attaches it to the balloon's string. The balloon's volume and the force required to keep the balloon at rest are measured. The valve is opened, releasing some gas from the balloon, and the measurements are repeated. The graph shows the data obtained. Describe how the graph could be used to determine the mass of the balloon and the density of the gas. Okay, so in this one, I went back to my original equation, except instead of writing F net, I wrote FT. So this FT, this tension force, is what's keeping the balloon in place. And then I was able to write out the same things as before for the buoyant force and the force of gravity. And let's see. And then what I did was I distributed this term here. So I multiplied out the G, and then I rearranged this. I put the rows together and the volumes together so that I could factor out VG. And when I look at my graph over here, what I notice is that this force on the y-axis is the tension force. And I notice that volume is on the x-axis. So when I overlay this with y equals mx plus b, what I see is that v is my x variable. My slope is the change in is the difference in densities. It's actually the difference in densities times g, because we've still got this g hanging out here. So I would need to divide by g before I calculated that. And then the y-intercept is the mass of the balloon plus the string times g. So here's my y-intercept, and it's the mass of the balloon plus the string times g. So I could divide the y-intercept by g to get the mass of the balloon plus the string. So again, you have to say how you would get both the mass of the balloon and the density of the graph, and you get them from the slope and the y-intercept. And then this is how the points are distributed on that question. Okay, moving along here. This question I found very challenging because it's ambiguous, and I'm going to talk a little bit about the ambiguity. And I wish I could give you total clarity, but I'm not sure that I can. I also wish we could have a conversation face to face. So if you have ideas, please post them in the discussion. I'd love to hear them. Okay, so this question is a short free response question. Show your work for each part of the question. This question is worth 10 points, suggested time 20 minutes. One section of a 5-meter wide irrigation channel that is filled with water contains an incline as shown. At the top of the incline, the channel is 3 meters deep and the water has a speed of 2 meters per second. At the bottom of the incline, the channel has a depth d and the water has a speed vb. So all we know here is that the depth has changed and that the speed has changed. In a coherent paragraph length response, explain how the changes in the channel affect the pressure of the water in terms of the energy changes of the water. Okay, so I'm just going to do a little quick review here. Bernoulli's principle tells us this. Oops. Let me do it this way. So I'm just practicing writing out Bernoulli's principle, and if you haven't done this lately, I encourage you to do the same. Okay, so this side would be at the top, and this side would be at the bottom. And these pressures that pressure changes depending on the speed and the height or the depth. And I'd like to remind you that Bernoulli's principle or Bernoulli's formula is really a statement of conservation of energy. And so remember that pressure is force per unit area, and these other values are density related, so they're like mass per unit volume, and you can see how the quantities are related. And so what happens here is when kinetic energy, remember that speed is related to kinetic energy, and when gravitational potential energy, which is related to height, when those change, the pressure also has to change. And so it's important to note that pressure changes as a result of the fact that energy is actually conserved in this process. So as the water gains kinetic energy as it flows down the ramp, the pressure changes as a consequence of that. Now, one thing that's really tricky about this question is we don't know how the depth changes, and we don't know exactly how the speed changes. We know that the water going down the ramp is going to make it speed up. We do know that. But we can't tell if it's being squeezed. Like, we can't tell just by looking at this. We can't tell if this is shorter or taller. So that's a little frustrating. And so part of our answer can be sort of precise and part of it is kind of ambiguous. So one thing that we do know is we know that the change in height decreases the gravitational potential energy, and that's going to increase the pressure of the water. So this is kind of like gauge pressure. And you'll recall gauge pressure is just the fact that if you have, any vessel of water, then the deeper you go in the water, rho GH, the more pressure there is. And if you've ever swum to the bottom of a pool, your ears know what I'm talking about. Okay, now the next part we can't really tell because we don't know this cross-sectional area. So all we know here is that the speed of the water changes. We don't know if it goes up or down, but we know that the change would change the kinetic energy, and that also would change the pressure. So those are two important components of the answer here. The third important component is to say that Bernoulli's equation tells us that the sum of the pressure, the kinetic energy per unit volume, and the gravitational potential energy must be constant, that we have a conservation of energy. And then finally, this answer is supposed to have some linking it all together, since gravitational potential energy and KE, kinetic energy, change, the pressure must also change. So this question is supposed to be answered technically in a paragraph. I wrote out full sentences and I made them bullet points so that you could see what points were awarded for. And again, this one is a little bit ambiguous, and therefore it gives us a sense of discomfort, but I encourage us all to work through it and know that we're probably going to see things on the exam that give us that little bit of discomfort. We can do it. We're going to work through it anyway. Okay, let's try this one. Last one, part B. The lower part of the channel gets narrower. Okay, thank you. Now they're giving us some clarity. As shown in the figure, the shaded area is a slice of water in the section of the channel that is getting narrower. The following shape represents a side view of the slice of water. The water is moving to the right. On the shape, draw and label the vectors representing the forces, not components, acting on the slice. Represent each force by a distinct arrow starting on and pointing away from the shape. The vector should indicate whether the forces have the same magnitude or different magnitudes. So if you've ever sprayed a hose and put your thumb over the end of the hose, you know that the water will speed up through this narrower opening. And what happens is, part of the reason for that is that there's going to be higher pressure on the left and lower pressure on the right. And you may recall when water speeds up, we have lower pressure. So in my diagram, you'll see that the pressure coming from the left is greater than the pressure coming from the right. And there is pressure on both sides. The other thing you'll notice is our good old friends, the normal force and the force of gravity are equal and opposite. And the reason for this grid is for you to carefully show that those are equal. So I chose to make this 3 units long for FG, and I would make it 3 units long for FN. Okay, I hope this was helpful. I know it was kind of long-winded. I would appreciate any comments, ideas you guys have for me improving my instruction for you. And thank you for the time that you're spending on this. And I hope you're doing well. And I will